Hello everybody, and welcome back to another Big Ideas lesson. Today we're tackling section 4.1, polynomial functions. Let's get to it. Before we can talk about a polynomial, the most important thing we can talk about is actually something called a term. A term is basically another name for a symbol or cluster of symbols multiplied or divided. So as long as you have a bunch of things that are being multiplied or divided together, it's a term. So an example of a term might be the number 3. That's a term because it's just a symbol, it's a number. Maybe I have 3x. Remember that 3x is 3 times x. I could have 3x squared. 3x squared is the same as 3 times x, so it's all being multiplied. I could have something crazy that looks like this, like 9xy over z to the 5th, and it's still just a term because everything is being multiplied or divided. However, the instant I add a plus or a minus sign, we no longer just have one term, we have two terms. Here's term number 1. Here's term number 2. So the important thing to note is that terms are separated by plus or minus. An example would be something like 9x cubed plus 2x. We have a term here, and we have a term here. When we put a bunch of terms together, we get a polynomial. The definition of a polynomial is a monomial, which is another name for a term. So you might hear me say the word monomial. That just means a term. It's a monomial or sum of monomials. So this thing that we wrote down is a polynomial because it's got more than one term. Polynomials can be written in a whole bunch of different ways. So maybe I have a polynomial that's 2 plus x cubed minus x squared. That's a polynomial. In fact, how many terms does this polynomial have? It's got 1, 2, 3 terms. However, a polynomial function is something very, very specific. You see, notice how I kept on having these different powers. The reason for that is, if I was to have multiple terms with the same exponent, like 2x plus 5x, we could just combine these into a single term. You can't do that if you had 2x squared plus 5x. These cannot combine. You could factor them, but you can't combine them. This is why we want to generalize our rule. So polynomial functions will look like this. Now, this is a formula that we're going to see, but we're not going to utilize. The idea of a polynomial function is, we always want to write out all of our terms as having a bit in front, a variable, and an exponent, right? Let's start with the bit in front. I'm going to call this a, and we want to multiply it by some variable, x. That's fine in its own right, but we also want to give a variable that tells us, hey, you're allowed to have an exponent. So let's use the variable n. N stands for the number of the exponent. So if n equals 9, this would be x to the 9th. We're also going to label our a with this n as well. So it tells us, hey, here's the number that's multiplying our nth term. Well, we already have 9, for instance, would be our example here. How can we write 8? Again, we want to have a number times our variable, but we can't just use the letter n again, because otherwise we can combine them. We need a new variable. Let's use n minus 1. If n was 9, n minus 1 would be 8. And we could keep going down. We could do n minus 2, we could do n minus 3, but eventually it will reach a point where we're left with a final term. Something that doesn't have a variable, or an exponent. Something that'll just be to the 0 power. This is a polynomial function. Before we get too ahead of ourselves, I want us to talk a little bit more about kind of the biology of these terms. Let's talk monomials first. A monomial has 3 pieces. The first is the number in front. What do we call a number that multiplies a variable like this? Well, we've always called this a coefficient. A coefficient is another name for a number that multiplies our variable. Speaking of, this part is the variable. The variable is just a letter. And what do we call this 4 that's hovering above our variable? Well, we know that that's called an exponent. So every single term can be written as some coefficient times a variable to the power of something. Even the number, let's say 2, even that can be written out like this. Think about it. What exponent could I have that would make my x value disappear? We could write it as 2 times x to the 0. You may recall that x to the 0 is just 1. So everything can be written like a term. A polynomial is a little different. We still have some important pieces, but it's different for what's important to us. First things first, once again, we do care about the number that's in the front. But it's the number that's in the very front of this polynomial that matters the most. It's a coefficient, but there are a bunch of other coefficients. There's -4, -2. This coefficient is in the lead, so we call it the leading coefficient. It's whatever number is at the very front of your polynomial after you put it in the right order. We'll talk about how to do that in a little bit. And we have an exponent here, but we actually want to start talking about the biggest exponent. The biggest exponent is the only one we really care about, and we call it the degree. Finally, the last thing we care about in a polynomial is the last number, the number that's all by itself with no variables. This here, this last little bit, is called the constant term. If you have a number at the back with no variable, it's called the constant term. If you don't see a number in the back with no variable, that means our constant term is 0. We're adding 0 at the end of this. I mentioned the word degree, and this is where the variables and the exponents really do matter. In a polynomial, we might want to talk about these and say, what's the biggest term we have here? Well, the biggest all depends on that exponent. It's called the degree. The degree of a term is just the number of variables in a term. And it just shows us how big a term is. Like, I could give you the following term. I could give you 2x squared y cubed. And if we count up all the variables here, this is the same as 2 times x times x times y times y times y. That's degree 5. There are 5 variables. The degree of a polynomial is a little different. Like I said, we only care about the highest exponent. The degree of a polynomial is the highest exponent, or the biggest degree term. In this bottom example here, we have x cubed, x squared, x to the first. Well, this one has 3 x's in it. This one has 2, this one has 1. This here is the most powerful term. We would call that degree 3. So maybe I give you the following polynomial. Let's say I gave you 2 minus x to the fourth plus 2x squared minus 3x to the sixth. Well, again, we only care about the highest degree polynomial. The 6 is the highest, so this would be a degree 6 polynomial. But wasn't it a little weird how I wrote it this way? It looked much nicer down below back when we had all of it in order, because it lets us know, hey, this one's the most powerful. This is where the standard form of a polynomial comes in. The standard form of a polynomial is a polynomial written from highest degree to lowest degree. We write it from the highest degree to the lowest degree. Let me give you that example one more time. Let's say I had 2 minus x to the fourth plus 2x squared minus 3x to the sixth. If I wanted to write this out in standard form, we would have to change it slightly. We would have to make it so that our highest degree term is first. The negative 3x to the sixth should go first. What's the next highest degree? We've got a minus x to the fourth here, so we write minus x to the fourth. Next we have a plus 2x squared, so that should go next. And then we should put our plus 2. The reason we write it this way is because now we can easily see what the leading coefficient is and the constant term. We're going to talk about end behavior in a little bit, but I want us to get some practice to see what types of problems we'll actually see during class. Before we do, there is one last thing I want to show you. This table here. This table here shows us a couple of different types of polynomials that we might see. And it's important to identify these because, as they come up, these polynomials might have different shapes. So for instance, this first one, f of x equals negative 14, if I just graph negative 14, it's just going to be a line at the number negative 14. Okay, nothing too crazy yet. What happens if I was to write out the next one? Next one we have is 5x minus 7. Give me just a minute to type that one up. 5x minus 7, as we know, is a straight line. We call any function that gives us a straight line linear. So anything with degree 1, anything that doesn't really have an exponent on our x, but still has an x, is linear. We also learned from the past 2 units that anything with an x squared is going to give us something called a quadratic, which looks like this. It's a parabola, right? We call it a quadratic. But we can go even higher. The next step up is something called a cubic, and it's called that because we must have a cubed term somewhere in there. So here, for instance, we have x cubed. This graph is going to look a little strange, but here it is. It's kind of like an S shape. You're going to hear me call this the snake. Oops, I just realized I accidentally missed a little sign in here that made the graph look weird. It should actually look like this type of snake. It's almost like a straight line, but it's got a little curve in it. This is going to be relevant later. Last but not least, we have something called a quartic. And a quartic is when we have a fourth power somewhere in there. Now we can go higher, but quartic is going to be the last one that we see here. If we take a look, oh, how weird is this? It's like a parabola, but the middle bit is a little lumpy. You're going to hear me refer to this as a lumpy parabola. You will be able to memorize all of these pretty easily once we start to find the rules. But before then, let's just talk about standard form. I want us to write the following in standard form. State the degree of the polynomial, the type of polynomial it is, the constant term, and the leading coefficient. None of these should be done before you put it in standard form, because you never know if something can simplify. So, I'm going to show you how to do the first one. From then on, I want you all to try the next two. To put this in standard form, we ask ourselves, what's the highest degree term? It's x squared. So we should write x squared plus 9. What degree is this? Well, it's degree 2. It's squared. So this should be 2. What type of polynomial is a degree 2 polynomial? According to our table, when we go down to 2, we call a degree 2 polynomial a quadratic. And now that it's in order, we can see what the constant term and the leading coefficient are. In this standard form, the constant term is the number that doesn't have a variable. So our constant term is just 9. The leading coefficient is the number in front of our x squared, but we don't really have one, do we? Remember, if you don't see a number in front of your variable, you can put the number 1. This is like 1 times x squared plus 9. So it's just going to be 1. Pause the video here, try out these two, and if you would like, try out example number 2 where we're evaluating. Pause the video, try these problems out, and come back once you're done. How'd we do? This was a quartic of degree 4. You see the constant term is the number by itself. The leading coefficient was -1. You could put a 1 there if you like. This one over here was weird because it's a cubic, but there wasn't a number by itself. That means we can imagine there being a +0 there, because a +0 wouldn't change the problem. That'd be our constant term. Example 2 says to evaluate a polynomial. We have to remember what evaluate means. Evaluate just means plug in. So this is asking us to plug in 3 for x. If we were to simplify this all out by putting it in our calculator, it's a lot to do, this would equal 98. For instance, 5 times 3 would be 15. 3 squared times -8 is -72. 3 to the 4th times 2 is 162. We start to see how we get 98 here. All right, let's flip the page. Actually, let's flip, well, no, we'll see this in a second. We're now going to talk about the end behavior. The end behavior of a graph is the most important thing we can do when we're looking at a picture of a graph. The reason is, the end behavior tells us what directions our graph goes in, our polynomial. It's determined by two things: the degree of the polynomial and the sign of its leading coefficient. So exploration 1 is, using your graphing calculator, let's fill out this table. I've filled in a couple spots for you to help out, and I've shown you what the first column will look like. So if we look at the first one, we see that we have 3x. That's just degree 1, because you can imagine there being x to the first power there. The sign of our leading coefficient, that's what LC stands for. Our leading coefficient is 3. Notice that it was positive, so that's +3. I sketched out the graph here. Technically, we should also draw arrows, because these arrows show us the graph goes on forever. And now we want to find the end behavior. The end behavior is found by looking at the graph and seeing what happens on the left side of it and on the right side. So on the left side of the graph, we see that we have an arrow, and it's going down and to the left. So I drew an arrow down and to the left here. It's going down towards negative infinity. This arrow is going up and to the right. The right behavior is up and to the right. What I'd like you to do is I'd like you to pause the video here and try to graph some of these. Just graph them for right now. We can fill in the data later, but I want you to graph these and sketch what the graph should look like. Try it out. Did you get a chance to try it? If not, I do want us to really try this, because otherwise we're not going to learn it the same way. However, let's see what these graphs look like. So 4x squared minus 2x looks like a parabola. It starts from the top, goes down, and goes back up to the top. Next up, we have our cubic. And our cubic is going to give us this weird S shape again. It's like a weird snake is what I call it. And this snake happens to go up, then down, and then back up again. So it's going down here, it's going up here. Next up, we have our quartic. And I think lumpy parabola is an underestimation here, or understatement. We get this like W shape. It's like a parabola, then it goes wow, right in the middle. So it starts up top, going towards the left, and it ends up top, going towards the right. Last but not least, we don't really have a name for a fifth power. We could call it a quintic, but for anything more than 4, we'll usually say just a polynomial of degree whatever. So this is what a polynomial of degree 5 might look like. It kind of looks like a snake again. Goes here, levels out, goes down, and goes right back up again. Let's track the end behavior here. So if I look at this parabola, on the left it's going up and to the left, so I'm going to draw an arrow this way. On the right it's going up and to the right, so I'm going to draw an arrow this way. This one's going down and to the left, and up and to the right. This one's going up and to the left, and up and to the right. This one's going down and to the left, and up and to the right. We might start to see a pattern here. Before we do, I want to show you the rest of the table, because there are some important things to notice. Our degrees just went up by 1 every time. Again, the degree is the highest exponent. And the signs of our leading coefficients were all suspiciously positive. What are some patterns we might see? Jot down a couple of patterns you might see in the table. Then, try to see if you can use those patterns to predict what x to the 6th might look like. Hopefully we're trying this one out and writing these down, but if not, I want to share a couple of things we might notice. The left behavior changes from down to up to down to up to down to up. So left behavior goes from down to up, to down, to up, to down, to up. It changes. But the right behavior does not. The right behavior is just up and up and up and up again and up again. That's an important pattern to notice. The other thing to notice is odd degrees give snakes. Even degrees give lumpy parabolas. So all of our even ones are just lumpy parabolas. All of our odd ones are sort of like snake shapes. In fact, we could probably predict what x to the 6th will look like based on those rules. It looks like it's going to go, according to the pattern, down, up, down, up, down. It's going to go up and to the left, it's also going to go up and to the right from what it looks like, and it's going to be a lumpy parabola since the 6th power is even. And if we graph it, let's see. Yes, it is! We end up getting a lumpy parabola. Let me actually zoom in so we can see it even better. There we go. It's like a parabola with a lump in the middle. So x to the 6th is going to be a lumpy parabola up and to the left, up and to the right. That's the end behavior. So back on that first page, when it asks for what the end behavior is, the end behavior is just going to be what the parabola looks like on either end. It's the behavior of the parabola as it goes towards the end. Try doing the same thing with the bottom table. Pause the video and see what happens when we have a negative leading coefficient. Try it out. Welcome back, and hopefully we've seen that with the negatives, our graphs flip backwards. So our snake for this one, for the cubic, is going to look like this. Our parabola for the 4th one is going to be sort of upside down and lumpy. Our snake for the 3rd one, or sorry, it'll just be an upside down parabola. What am I talking about? This will be a straight line. This will be an upside down parabola. This one is going to be the weird snake. This one is going to be a lumpy parabola that's upside down. And this one's going to be a super weird snake. Here's the general rule of end behaviors. Any polynomial that's degree is odd has end behaviors which go in different directions. Any polynomial whose degree has is even will have end behaviors that go in the same direction. If your leading coefficient is positive, its right end behavior will go towards positive infinity, so it'll go up. Notice how to the right, if we have a positive leading coefficient, it goes up. If we have a negative leading coefficient, like if the number in front is negative, it's going to go down as it goes to the right, no matter what. Without graphing, can you try to determine what the end behaviors of these polynomial functions are going to look like? You might need to put them in standard form first to really tell. Once again, pause the video here and try to see if you can use those rules about positive coefficients, negative coefficients, and the directions of their end behaviors to help you here. These 4 rules can tell you what the parabolas will look like. Pause the video and try it out. Let's talk about some of these. To determine the end behavior, we care about the degree and we care about the leading coefficient. With an even degree, we know it's going to be a lumpy parabola. So our ends are going to go in the same direction. That negative leading coefficient tells us that it's going to be a lumpy parabola that goes down like this. Our degree is even, our leading coefficient's negative. It's going to have 2 ends that go down. So both left and right go down to negative infinity. On the next one, we see that we have an odd degree, and we don't have a negative leading coefficient. It's positive. It's positive x to the 7th. The 7 tells us it'll be a snake. Remember that odd polynomials look like snakes. So we know the 2 ends are going to go in different directions. It's going to be like one's up and one's down, or one's down and one's up. And since we have a positive leading coefficient, the positive leading coefficient tells us it'll go from down to negative infinity and then up to positive infinity. So the left goes to negative infinity, but the right goes to positive infinity. This table is how we determine these. Last but not least, this one is crazy, but again, we only care about the degree and the sign of the leading coefficient. The degree of 145 is odd, so it's going to be another snake. It's going to be one of these two. And again, our leading coefficient is positive. Since our leading coefficient is positive, it's going to look like this, where on the left it goes down to negative infinity. The left goes to negative infinity, and the right goes to positive infinity. It's going to look like this, with a bunch of squiggles in the middle. Last but not least, we now have the basis for what we need to actually graph a polynomial function. The first step is to plot points to determine the shape of the graph's middle portion. Let's start off there. So to graph this, we need to plot some points, right? In other words, we need to pick a bunch of points to graph in the first place. What I recommend is picking at least 5 points to do this with. And I also recommend not just having positive numbers, but throwing some negative numbers in there as well. The numbers I'm going to choose for today are -2, -1, 0, 1, and 2. Remember how we learned to evaluate? We are now going to evaluate this function with each of these points individually. So to figure out what y should be when x is -2, we can say f of -2 is going to equal -2 cubed plus -2 squared plus 3 times -2 minus 3. Again, you can pick whatever points you want, but points like this are very nice for telling us what the graph will look like. So when we evaluate this, -2 cubed will simplify. -2 cubed is -8. Well, -8 is just 8. That's plus -2 squared. Well, -2 squared, that's just going to be +4. 3 times -2, that's going to give us -6, so it's -6. And then we have -3. 8 plus 4 is 12, -6 is 6, -3 is 3. So we get the point -2, 3, and we can plot that. Try to fill out the rest of this table and plot those points, and then we'll talk about how to determine what the graph will look like. Try this out and sketch the graph. How'd you do? We should have gotten the following points for our y values. 0, where it was -1. Where it was 0, we should have gotten, we should have gotten 4 there. I mixed it up. We should have gotten -4 there. We should have gotten -3 here. We should have gotten 0 here. We should have gotten -1 here. So when we plot all of these points, we get something that looks very weird. We get -1 down to -4, so it looks like our graph goes down here somehow. Then it goes 0, -3, so it goes slightly up. Then it goes 1, 0, so it goes right here. Then it goes 2, -1, so it's down again. This looks super, super weird, and that's okay. Your points are not going to make much sense. But we can still graph this, knowing what we know about the end behavior. We want to use what we know about our end behavior to sketch the graph. So how do we find that end behavior? Again, we see that we have our leading coefficient is negative. We see that our degree is odd. So we know that it's going to be something like this, where the left side goes towards positive infinity, and the right side goes down to negative infinity. Without exactly knowing what the graph looks like, we know at the very least that it's going to go up and to the left, down and to the right. We just need to make a graph that shows that. This is where you can use a little bit of interpretation. You still want your graph to be as smooth and simple as possible, but we want to connect these points in a way that starts up at the top and goes down to the bottom. So I'm going to try this out, and I'm going to make mine look like this. It's going to go down, it's going to loop up, it's going to go down again, and that's my interpretation of what this graph might look like. Might not be exact, but we're starting at the top, we're ending in the bottom, and we've connected all of our points. That's all that matters. In fact, if I graph this, this is what the actual graph looks like. Aren't we pretty close? I think I made this part a little bit too wide. I think this part's supposed to slope down a little bit more, so it's more like a swoop. But overall, pretty good job in my opinion. This is how we can graph these polynomials. We plot some sample points. We use the end behaviors to tell us what it looks like. The last page is just like this as well. I'm going to leave these ones for you to try. Then try to see if you can do the last problem. Pause the video and try these ones out for yourself. Let's do it. So here are the tables that I got just using my -2, -1, 0, 1, 2. Those are like my old reliables, but you can use whatever points you like. I didn't graph -2, 12 because that would be all the way up here. Like, it'd be all the way off the graph. So I just want to keep my points on the graph, but I do know that it goes up that way, right? In fact, let's determine the end behavior to find what the graphs look like. Here, this is x to the 4th power, and we have a positive leading coefficient. We know that a 4th power is going to be a lumpy parabola. And we know that if there's a positive leading coefficient, both left and right go up. So it's going to go up to the left, up to the right. Our graph is going to probably look something like this. Here's my interpretation. Goes down, goes up, goes down, and since we want it to go up again, we can just swoop it back on up. Very shaky looking parabola, but it'll do. It's our guess. Next, we have degree 3 and a leading coefficient of, again, +1. Made these ones easy. Since it's positive and it's degree 3, we know it's going to be a snake that starts down low and ends up high. So I'm going to make my graph look like this. So it'll go up, and down, and up again. If you actually graph these two on your graphing calculator, you get pretty close to these interpretations. Mine's a little bit too pointy here, and a little shaky in the middle. But overall, these are pretty good guesses, right? This is how we graph parabolas. Last but not least, for this word problem, once again, we are given a function, and we need to graph it. So, we want to use our graphing calculator to graph this function and determine the behavior. Then find the average rate of electric vehicle, or average rate of number of electric vehicles in use. Then find and see, do you think this model can be used for years before 2001 or after 2010? And when you graph this on your calculator, you're going to get something a little weird. It almost looks like a straight line. It's not very descriptive. In fact, even if I zoom out a little bit, Again, not very descriptive. I have to zoom out a whole bunch more before I even start to see how this thing curves. And we see it right there. That curve happens very, very far away. But here on our 0 to 10, we see that it just goes straight up. So on this interval, we can say it starts down and to the left, goes up and to the right. What was the average rate of change in the number of electric vehicles in use from this time? But we have to remember what the rate of change means. The rate of change is interesting to say the very least. The rate of change, remember, is like the slope. We need to find the slope. So here's what I'm going to do. I'm going to set up my graph using the window button. I clicked on the window button here. And I'm going to set it up so my lowest x is 1, my highest x is 10. I'm going to set it equal so that, or set these numbers, I should say, equal, so I can see the y values from around 0 to 65. And if I graph this, we can see a little bit more clearly what's really happening here. It sort of goes up then levels off, right? To find the average rate of change, we can use our slope formula from Algebra 1. Remember that slope is rise over run, or y2 minus y1 over x2 minus x1. Well, this gives us a way of finding the average. We can look at our table to figure out where it started at. So at time of 1, it was at 18.584. I'll have that be my y1 and x1. So I'll have this be 18.584. At 10, which is the last place they want us to look, it was 58.57. We can now find the average rate of change by basically finding the difference between these 2 points. I'm finding the difference in their x values and the difference in their y values. If I do this in my calculator, we should get the following. We should get that this is going to be, maybe not equal to, but around 4.443. Remember that the average rate of change is like your slope. But we haven't seen that in a very long time, so that's why we're practicing it here. Do you think this model can be used for years before 2001 or after 2010? Well, it's sort of difficult here, right? The end behavior seems to imply that we could. Like if I was to zoom out once again, let's make my window a little bit bigger so we can see more of the actual graph. Let's make it so my x maximum is 20 and my y maximum is, I don't know, 200. If I was to see the graph here, we see that it looks like it's pretty reasonable on that side. But if we keep zooming out, how many people are really going to buy electric cars? If I zoom out so my x maximum is 200, my y maximum is 2,000, is it reasonable to assume that 2,000 people, 2,000 times are going to buy more cars? It's not reasonable to continue with this. This is saying that in 2011, it would be so many electric cars being bought. 63 cars, 71, 100, 200, 300, 1,000. It goes up by such a huge amount, it's just not reasonable to assume that it continues. Especially, I think, oh yeah, since it says in the thousands, it's even higher. This is saying that as we keep buying cars, this is the number of thousands of electric cars bought every year. It'd basically be saying that in 2022 alone, people are buying 542,000 cars. In my opinion, in the short run, it makes sense. In the short run, it makes sense. because we can go up exponentially just fine. Just once you start reaching numbers like this, it gets a bit ridiculous. But the question is also, what happens before 2001? Let's look back at our table and see the number for x before 1. So at the year 2000, people were buying negative 2,000 electric cars. And at negative 1, people were buying negative 29,000 electric cars. It immediately breaks down because we can't have negative electric cars. Can't have negative electric cars. In total, here's what this problem tells us. Number 1, our graph looks like a snake. It goes from down to the left, up to the right. Number 2, on average within those 10 years, this is about how many cars are purchased. For letter C, the graph makes sense as you keep going forward, but it doesn't make sense as you go backwards because you can't buy negative electric cars. If you would like more practice with these, on the next page, there is some extra practice that you are able to do. However, that'll be something that you can do on your own, and you can feel free to ask me any questions you might have. For now, that is the end of our notes for today. I want to wish you a very good rest of your day, and I will catch you next time. Take care.